rational root theorem. We've already learned the conjugate root theorem. At the end, we're just going to review that and re-go over the conjugate root theorem. But today we're learning the rational root theorem. This is a way cool thing for us, guys, because we can use this to solve so many different types of polynomials. So what we're learning today is really going to help us in our future with math. Okay, so remember that rational means fraction. So rational root theorem. So rational means fraction. So 2/3 is a fraction. Negative 3/4 is a rational number. 2/3 is a rational number. So that's a rational number. That's a rational number. That's a rational number. 1/2 is a rational number. 5. That's still a fraction. Technically 5 is 5/1, right? So 5 is technically a rational number. Does everybody understand? Negative 20, that is written as a fraction. Technically, negative 20, yeah, it's a whole number, but it still could be written as a fraction. It's the same thing as negative 20 divided by 1. So the rational just means can be written as a fraction. So it's any number that could be written as a fraction, which includes whole numbers. Okay, so here is the rational root theorem. It's going to seem a little bit like what at first, and it will make more sense once you see me do it. Okay. So think about it, guys. Factoring a polynomial. The whole reason we learn factoring is so that we can set our linear factors equal to 0 and solve for x. So we're finding the x-intercepts. And that's the whole point of factoring. So why have we learned factoring all these years? So that we can simply find zeros. We can find the roots. But once we get into these really high order polynomials, it's kind of hard sometimes to find the roots. Especially when we have something really large in the front, the leading coefficient, something really large, and some number that's really large in the end. Our constant's really large. That's really hard to factor a lot of times. Now we could sit and do a guess and check method, which would take us forever, because there's an infinite number of roots we could have. So the rational root theorem, guys, just gives us a way to kind of simplify the amount of roots that we could be looking at for our answer. Alright, so here's the rational root theorem. Now it looks really complicated right here, but it's really not, so don't let it scare you too much. But hopefully pay close attention to this because you'll need to understand it for the next part. So, here is the rational root theorem by definition. Obviously the math makes more sense once we do it. So let p of x, so let's have a polynomial equal to a sub n of x to the nth power, so that's just our leading term. So they're not specifying because it could be any, it could be like a 5th degree, a 6th degree, a 7th degree, whatever. And this could be any number, plus da da da. So it could be a polynomial of any size. That's just how they write out this big long polynomial. So let p of x equal to that be a polynomial with integer coefficients, meaning whole number coefficients. There are a limited number of possible roots when p of x is set equal to 0. Okay, so rational roots must have the reduced form p divided by q, where p is the integer factors of a sub naught, so p is the factors of this nth term here, and q is a factor of a sub n. I said a sub 1, but I meant a sub n. Of a sub n, so this front thing. So then you'll list out all your factors of this n thing, you'll list out all your factors of the front thing, what multiply to be it, and you'll take all possible forms of p divided by q. So p divided by q, all possible forms, including the plus and minus answers. Now I understand this is sounding like I'm speaking Chinese right now. I get it. But I have to talk about this till we actually do it. Okay, so now let's just practice this. If you have this somewhat like, okay, yeah, I kind of see what you're saying, then hopefully this will just make more sense to do it. Here we go. So we're just going to use the rational root theorem to list all possible roots for each equation, then find any actual rational roots. So looking at this, guys, what the rational root theorem means technically is we only have to look at the front term and the end term here. Everything else in between doesn't really matter for this part. Now this is the important part. The front leading coefficient, which is 2, that's going to be our q. Okay, that's going to be our q. And then this is going to be our p. This n term is going to be our p. Now we're going to list out factors of p and q. I'm going to start with p on top. Now if you set up your worksheet just like this, it's going to be a lot more organized. What multiplies to be 5? 1, right? So we have to account for the plus and minus. So plus and minus 1. And then also what multiplies to be 5 is 5. So 1 and 5. So plus and minus 5. Does everybody understand how 1 and 5 are factors of 5? The only factors. Okay, now we're going to list out, we haven't done the rational root theorem yet, Now we're listing out factors of q. What multiplies to be q? So obviously what multiplies to be 2 is plus and minus 1, and also the only other factor of 2 is plus or minus 2. Does everybody understand how I did my factors of p, my factors of q? All right, so now we're going to list out all possible p divided by q's. So now I'm listing out p divided by q, all possible. So you've got to take your p's and divide them by your q's. Now take my suggestion. Always start with one of the p's, divide it by all of your q's. Then you can move on. So we're going to do 1, let's start with 1. 1 divided by 1 is just 1, right, everybody? So that's 1 divided by 1, so plus and minus 1. We just took care of those two. Now we're doing 1 divided by 2, p divided by q. So we just took care of that q. So now p divided by q. So 1 divided by 2 is just 1/2. So we also have plus and minus 1/2. Is everybody following me so far? And now we're going to do all possible p's divided by q's. So we just took care of 1. Now we're going to divide 5 by all of our q's. So plus or minus 5 divided by 1. 5 divided by 1 is just 5. So plus and minus 5. And then also 5, so we've done that. And then 5 divided by 2 is 5/2. So plus and minus 5/2. Now that we've done all possible p divided by q's, guys, these are the only possible rational roots of our polynomial. So look, now we can see that it's either positive 1 or negative 1. That's a root, possibly. Positive 1/2 or negative 1/2 is also a possible root. Positive 5 or negative 5, also a possible root, and a possible 0. Positive 5/2 or negative 5/2 is also a possible answer. So now we have it limited down to these things. So it could be these. These are all possible. So now that we've listed all the possibilities, that's the rational root theorem. We've listed all the possible rational roots. Now remember, these don't account for imaginary roots. These are just rational roots, meaning can be written as a fraction. So if decimal, the square root of 2, if square root of 2 was a root, it wouldn't be listed here because these are the only possible rational roots. Okay. So we've listed the possible rational roots. Now we have to find any actual rational roots. So this is how, from here, your calculator does all the work. So everybody, here you go. So what we're going to do is pull up our calculator. We're going to graph this polynomial, and we're going to find the x-intercepts where it crosses the x-axis. So I go to y equals, and I'm graphing. So 2x cubed minus x squared. Make sure you type it in right. And then plus 2x plus 5. Okay. Hit graph. Now you might have to play with your window a little bit to see it better. Guys, we have to get good at playing with our windows. Okay, so everybody look at my graph here. It's crossing the x-axis. That's going to be a 0 as x value. Now it's crossing right there at that value. So I want to find out exactly what value it is. You cannot just look with your eyeballs and say that looks like it's crossing at -1. We don't know for sure where it's crossing. So you're going to actually use these functions on your calculator. So you're going to do second trace. And you're going to find the 0. Zeros are where it crosses the x-axis. So we're going to find the 0. Now there's only one 0 on this one. There's only one rational 0 here, or irrational, it depends. But there's only one answer here that crosses the x-axis. So only one real solution, I guess I should say. Okay, so left bound, hit enter, right bound. I'm going to let my calculator tell me exactly what value it's crossing the x-axis at. -1. So it is -1. So x is equal to -1. Now is that the only place it crosses the x-axis? Yes. Is everybody good with that? Okay. So x is equal to -1. So now at the top, we know that x is equal to -1. Was that one of our possible rational zeros? Yes. Okay. So x is equal to -1. So that's our answer. X is equal to -1. So all those other ones were just possibilities that we're throwing out. So these were all possible, and we only ended up with x is equal to -1. Now guys, if you plugged in -1 back into your function, you would get 0. That's why those work. You can always check your roots to make sure those are really your roots by plugging them back in, and we have 0 is equal to 0. So we would be good with that. All right, so does everybody see how we find it? It wasn't that hard, right? But it was just kind of different. Now understand something, guys. That doesn't mean there was only one answer. There was how many answers? We know for a fact there are 3 roots, right? Everybody, right? You go off the highest degree. But this is the only rational root. So there must be 2 imaginary roots. And we could go through and find them, but we'll do that at a later date. Because now that we know our roots, couldn't we use synthetic division to make this smaller into a quadratic? Synthetic division was dividing the polynomial. So we'll learn that tomorrow. But anyways. So, does everybody understand though that there are 3 roots, but the only rational root is -1. So there must be 2 imaginary roots. Does that make sense, everybody? All right, awesome. All right, let's do another one. It's a little bit different. So here we go. Use the rational root theorem to list all possible roots for each equation. So here's this big equation. Now, once again, the reason we're learning this is because we wouldn't know how to solve this otherwise, because if we tried to factor by grouping, it wouldn't work, so we have to still be able to solve it. So we use the rational root theorem to list out all possible rational roots. All right, so once again, the most important thing is you get Q and P correct. That's our Q, that's our P. Now just start out by listing out your factors. I always put P on top because you're going to be doing P divided by Q, so it just flows better. So let's list out all the factors of P, don't miss any. Plus and minus 1, what else multiplies to be 8? Plus and minus 2, plus and minus 4, and plus and minus 8. Those are all my factors of 8. Is everybody comfortable with that? And then Q. All the factors of Q. Plus and minus 1, what multiplies to be 3, plus and minus 3. So now we're going to list out all possible rational roots. So we're doing all possible P divided by Q's. So don't miss any. You got to be really careful. 1 divided by 1 is 1. So plus or minus 1. 1 divided by 3. So 1/3 plus or minus 1/3. So I just took care of 1. Now 2 divided by 1 is just 2. So we can also have plus or minus 2. This one's a lot bigger. Plus or minus, and then 2 divided by 3. P divided by Q, so 2/3. So plus or minus 2/3. All right, we just took care of 2. 4 divided by 1 is 4. So plus or minus 4. 4 divided by 3 is 4/3. So plus or minus 4/3. We just took care of 4. And then 8. 8 divided by 1 is 8. So plus or minus 8. And then plus or minus 8 divided by 3. Okay. Is everybody good with that? Now those are a lot of possible rational zeros. So now you're going to take your calculator, graph it, figure out which one of these, if many, and there might be more than one, that is your rational zero. Now keep in mind there should be 3 solutions, but that doesn't necessarily mean they're rational, which means can be written as a fraction. So let's see if there's any rational solutions here. We use our calculator, we graph the polynomial, and see which zero we are going to be looking at here, if any. So y equals, so we have 3x cubed plus 7x squared plus 6, oh crapola. I hate these way advanced calculators. They're a bigger pain in the butt. Okay, there we go. 3x, holy schmooly. 3x cubed. I don't know if it's going to say error if I don't delete that box. We'll see. Okay, there we go. 3x cubed plus 7x squared plus 6x minus 8. And I hit graph. Once again, you might have to change your window so you can see it better. If you need to get in closer, make it a smaller window. Oh, it's only crossing in one place again. All right, so let's figure out what what number that is. So you do second trace, and I find I'm going for 0 because that's what we're looking for, is the 0 where it crosses the x-axis, which is a 0. So it's asking me for a left bound. I hit enter because I'm left of it. Right bound, make sure you're right of it. I'm right of it. Hit enter. Enter again. So it's at 0.666667. 0.666667. Okay, so 0.666. That is one of our zeros. So I'm going to write that up to the top. Now, if you do it on your paper just like me, this will really help you. So I know the actual root is 0.66666. Okay? Now, which decimal in here matches up? So this is where you're going to have to take your yes, but this actually might be able to change into a fraction. One of these might be equal to that. So, take your calculator. We obviously know it's not a 1, right? It's not 1. What's 1/3? 1 divided by 3 is 0.333. Is that? 0.333. No. 2, no. 2/3. 2 divided by 3 is 0.6666667. So 2/3. Was it positive 0.6666? So it's positive 2/3. Does everybody understand how that decimal is equal? 2 divided by 3 is the same thing. It's 0.6666. So our answer is 2/3. Positive 2/3. So that's our actual rational zero. There was only one in this case. Do you see how to do it? Do you need another example? Do you need another example? Yes or no? I have another one up. Okay, one more, then I'll let you work. Like I said, this is the only new thing. The next part you've already learned, so hopefully we'll be okay. Let's do one more then. Let's do one more. All right, so we have 7x cubed minus x squared plus 4x plus 10 is equal to 0. We're going to use the rational root theorem to list all possible rational roots. So the first thing you do is to identify q and p. That's q, that's p. List out all possible factors. I always start with p because it's p divided by q. So plus and minus 1, plus and minus 2. Well, multiplies to be 10, right? Plus and minus 5, plus and minus 10. Is everybody okay with that? Q, plus and minus 1, plus and minus 7. The only two things to multiply to be 7. So then we list out all possible p divided by q. All right, now understand something, guys. One more thing. Also, if you list out p divided by q, let's say we had 6/4, or let's say we had 3/2 listed. What if we got and we had a 6/4? Isn't that the same thing as 3/2? Everybody? So you won't list them twice. Does that make sense? Everybody okay with that? Okay. All right, let's do p divided by q. You guys tell me. So you guys speak up this time. We're doing 1 divided by 1, which is, so plus and minus 1. Then we're going to do 1 divided by 7, so 1/7. So plus and minus 1/7. And then moving on, 2 divided by 1 is 2, plus or minus 2. Does everybody see what I'm doing? P divided by q. Plus and minus 2/7. 5 divided by 1 is 5, so plus or minus 5. 5/7. So plus or minus 5/7. All possible p divided by q's. 10 divided by 1 is 10, plus or minus 10. And then 10 divided by 7 is 10/7. So plus or minus 10/7. All right, so now you'll graph it on your graphing calculator, find the actual zeros, and see if any of them match up with the possible rational zeros. Seven x cubed minus x squared plus 4x plus 10. All right, let's see here. Okay, once again, it's only crossing in one place. So you do second trace, find the zeros, left bound, right bound. Oh, it said error for some reason. I must have gone too quick. Second trace. Did anybody else happen to graph that? Intersect. Oh, I said intersect. That's probably why. So it's a 0. Left bound, enter, right bound. Okay, point. So it's crossing at negative 0.9209. Negative 9.209. Make sure you write in the negative. So I'm going to write that up here. Negative 9.2, oh, negative 0.9209. Now I've got to look at all of my possibilities and see which fraction matches up to that decimal, if any. If not, then it's not rational. No rational roots. So 1's not it for sure. That's not 1, obviously. 1/7. 1 divided by 7 is 0.14. So it's not that one. 2, it's not for sure. 2 divided by 7. I'm doing it in my calculator. 0.285. Definitely not that. 5, no. 5 divided by 7 is 0.714. So it's not that one. 10, no. And then 10 divided by 7. 1.4. So it wasn't any of these, right? Right? It wasn't any of these. So that must not be a rational number, meaning that can't be written as a fraction. So our answer would be no rational roots. No rational roots in this one. Because if it was rational, it would be one of these possibilities. The rational root theorem ensures that. Okay. Does everybody see how to do it? Yes or no? Because I have no idea if you even remotely understand this. Okay. So do problems 1 through 6. Once again, there are times you will have no rational roots. Ready, set, go. Check with me when you're done. Now show your work how I was, because it gets messy. And I'll be right with you. Let me push pause on my video, and then I'll be right with you. Okay, so we have learned this. The conjugate root theorem says. So recall that conjugates, just before we talk about the conjugate root theorem, what is a conjugate? Conjugate, guys, a lot of you just failed this on the first test. Conjugates have a change of sign in between the two terms. So these are some examples of conjugates. 2 plus 3i, 2 minus 3i. What makes them conjugates, guys, is the change of sign in between. It's only in between. So look at this. Positive 5i, negative 5i. Aren't those conjugates? Yes, isn't that technically 0 plus 5i, 0 minus 5i? Aren't they conjugates? Do you see a change of sign in between, guys? Okay. So negative 1 minus 3i, negative 1 plus 3i. What makes them conjugates is there's a change of sign in between. But look, my front two terms, my front term, my back term, front term, back term, they stay the exact same. So does everybody understand how the negative 1 has to stay the same? Okay, it's only a change of sign in between. So 1 minus the square root of 7, 1 plus the square root of 7. The conjugate is because it's a change of sign in between only. And then right here, these are conjugates, negative square root of 3 and positive square root of 3. Because it has a change of sign in between. So once again, I'm going to ask you, is this a conjugate? Negative 2 minus 3i and 2 plus 3i. Are those conjugates? No, right? This would have to be negative 2. Okay, good. All right, so the conjugate root theorem says if you have, pay attention, if you have an imaginary root or an irrational root, then its conjugate is also a root. Now the problem was the first time you guys heard this, you started doing some bad things. You said that whole number roots, rational roots, their conjugates were also a root, which isn't true. The conjugate root theorem says if you have an imaginary root or irrational root, then its conjugate is also a root. So 3 plus the square root of 7. That is an irrational root because it can't be written as a fraction. Try it. Do it in your calculator. 3 plus the square root of 7. Try to change it back to a fraction. It doesn't. So it's irrational, meaning it can't be written as a fraction. So its conjugate, 3 minus the square root of 7, must also be a root. Right here, 2i, that's an imaginary root. So its conjugate, positive 2i, must also be a root. Is everybody comfortable so far? Negative 2 minus the square root of 3. If you didn't know if it was irrational, you type it in. Negative 2 minus the square root of 3. Change it back to a fraction, and it doesn't. So it's irrational. So its conjugate is also a root. Well, what about 3/2? Is its conjugate a root?
Yes, it is. Yeah, 1.5.
No, conjugates only have a change of sign in between. So you don't change the first one.
Oh, sorry.
Right? So?
Yes.
Okay, guys. It's okay. Come on. Is everybody paying attention? 3/2 is a root. Is its conjugate a root? Is that an imaginary number, guys?
Oh, no.
No? Is that an irrational number? The definition of rational means written as a fraction. So irrational just means not written as a fraction. Can't be written as a fraction. Isn't that a fraction? Is its conjugate also a root? No! The conjugate root theorem says if you have an imaginary root. or an irrational root, then its conjugate is also a root. Are you guys paying attention to the little details here? Do you get what I'm saying? So if 3 is a root, is negative 3 a root necessarily?
No.
No, right?
No.
Okay, so a polynomial, p of x with rational coefficient, has the given roots. Find any additional roots of p of x. So here we go. Square root of 2, is its conjugate also a root? Yes. 1 plus I, is its conjugate also a root?
Yes.
So 1 minus I is also a root. What about negative 3i? Is its conjugate also a root? Is it an imaginary root? So its conjugate is also a root. If 4 is a root, is its conjugate a root? No, that's a number, a whole number. It's not irrational. It's not imaginary, it's not irrational. So what about 6 minus the square root of 5? If that's a root, then its conjugate must also be a root, right? Negative 2 plus 2i. If it's a root, its conjugate must also be a root. So negative 2 minus 2i is also a root. Is everybody comfortable with that? I'm confused at what's so hard about it. Am I not making sense? This is like one of the easiest things.
It's easy money.
I don't know if it is. 2/3, is its conjugate a root? No. Negative 5, is its conjugate a root? No. So this one has no additional roots. 6 minus the square root of 10, its conjugate must also be a root. What about negative 10i? Is its conjugate a root? 10i. How about 7? Is its conjugate a root? No. What about this one?
Yes.
Negative 3 plus the square root of 2. So are we getting the gist? Okay, so do problem 7 through 12. Ready, second? Okay? So guys, here we go. Everybody pay close attention. So it says, write a polynomial with rational coefficients so that p of x is equal to 0 has the given roots. So we have these 3 roots, but we might have more than these 3 roots. It depends. Do we have an imaginary root? Yes, then its conjugate is also a root. Do we have an irrational root? If yes, then its conjugate is also a root. So let's look. These are the roots. So these are the x values. So x is equal to negative 6, x is equal to 3, and x is equal to negative 2. Are there negative 2i? Are there any other roots?
No.
There's not. There's not?
No. 6. What?
If negative 6 is a root, is its conjugate also a root?
Oh yeah.
No.
Oh,
If 3 is a root,
positive 2i.
Okay.
Okay, you
So
can.
x is equal also to positive 2i. Does everybody catch my gist?
Yeah.
Okay, so these are our roots, right? These are our roots. So then we're working backwards to find the polynomials. So we're working backwards. Add 6. So we have x plus 6 is equal to 0. We subtract 3. So we have x minus 3 is equal to 0. We add 2i. So we have x plus 2i is equal to 0. And then we subtract 2i. So x minus 2i is equal to 0. We're going backwards here. These were the linear factors before we found the roots. Then from there, we multiplied them. Before we split them up, we had them multiplied. So then from there, take my suggestion, multiply 2 together at a time, and always multiply the conjugates together, because it'll just make your life easier. So let's multiply these 2 together first. X times x is x squared, minus 3x, plus 6x, minus 18. Right, everybody? Combine my terms, x squared plus 3x, minus 18. Is everybody following me? That's that piece. Now let's multiply this piece through. And since they're conjugates, won't their middle terms cancel out?
Yeah.
So I'm not going to multiply the middle terms. Yes?
Why did you get like a negative 2i at the beginning?
So we were given these 3 roots. So we know that if you have an imaginary root, its conjugate is also a root. Right?
So you have to do that forever.
We did do, that's the only rule, right? That's the rule for imaginary roots and irrational roots. Is 6 an irrational root? Nope, it can be written as a fraction, right? So its conjugate's not a root, necessarily. Does that make sense? The rule only works for imaginary roots and irrational. Right. Then you have to do the plus the conjugate root. Okay, so guys, this part, I'm only going to multiply the front terms, x squared, and the back terms because the middle terms cancel out. So minus 4i squared. What do we know about I squared? It's equal to negative 1. So we have x squared And then negative 4 times negative 1 is positive 4. Right? Almost done. Then we're going to multiply those two together. So we have x squared plus 3x minus 18 times, I'm going to put this down here, x plus 4, and then we would distribute. Guys, we should be able to do this at this advanced level. So we have x to the 4 plus 3x cubed minus 18x squared. We're almost there. 4x squared plus 12x, and then 4 times 18. So negative 18 times 4. Guys, are we good with this? Do I need to keep going? I feel like I'm just talking to the free air. Okay. And then we would combine like terms, right? We would combine like terms from that part. Do I need to keep going? Okay, I didn't think so. Okay, so look. I'm not going to go through this one, but given these roots, so x is equal to 4 plus the square root of 5, is its conjugate also a root? Yes. So x must also be equal to 4 minus the square root of 5. Then also, x is equal to 8i, and x is equal to, the conjugate must also be a root. So then from there, you'll bring them over accordingly, correctly. So be careful with these ones. Can we just grab them and float them over? No, you subtract 4, also subtract the square root of 5. So we would have x minus 4 minus the square root of 5 is equal to 0. So we're going to be multiplying out some hideous things here. Minus 4 plus the square root of 5. So we'll have x minus 4 plus the square root of 5 is equal to 0. And we'll have x minus 8i and x plus 8i. And then we'll multiply all those things together. Okay? Get that little shining grins off your faces. Just kidding, I love those grins. Okay, go for second. If I need to do number 16 with you, I will. Ready, set, go.
Nope. Do it.
Ready, set, go. A lot of these are quicker. Quick.
That word is legit. Yeah, but.
Shut up. So up.
X equals negative 3i. Now you bring them over. So you have x minus 3i is equal to 0. So you're multiplying x minus 3i times x plus 3i. You bring them over, right? And you'll have times x minus the square root of 6.
And the kid in the background? Yeah.
Times x plus the square root of 6. And then multiply each of those. Multiply these together. Multiply these together. Your middle terms will cancel out, but yes, there's going to be 3x. So you have x squared plus 3x minus 3x, and then minus 9x.
24 is plus first. Plus 24. Can I help you?
Okay, good. So then you just go, okay, you multiply through, you did x squared, but then you should have 3i times 3i, or negative 3i is negative 9i squared. Right?
Yes.
I
know you would. You're looking at a piece of pop, it's really good. Like,
and then right there you have
like that.
x squared, and then you multiply those two. You're done.
It's sort of looking
You're
small.
okay.
What? Nothing.
Negative 3i?
No.
It's just negative 3i.
Oh my pants.
Shut up.
But remember with those ones, your middle terms will cancel. You should have. You're almost there, except for okay. We'll cancel out. There should have been x squared minus 9i squared. I squared is equal to negative 1, right? So it would be x squared plus 9.
I'm just super depressed.
Oh yeah, number 16 is pretty. The square root of 36. Oh, you mean, okay, yeah. X square root of 6, yeah.
Yay.
First of all, x times x is x squared. Right here. Minus 9 I squared. I squared is equal to negative 1 is positive. No, what happened here? Oh, you have it. And now you'll distribute, double distribute that. Because they're not conjugates, right?
Oh, you toned down. Oh, yeah. So, oh, no, not carbon.
Okay, I'm going to do number 15 with you, not number 16. Number 16 is I mean, to be honest, if you're an way advanced learner, you should try number 16, but it's not a necessity. Okay, everybody, I'm going to do number 17 with you. If you can do number 16, you deserve a fist bump, because that one's pretty tricky. Alright, so here we go. Number 17 I'm doing. So we have x is equal to negative 5 and x is equal to 3i. Are there any other roots I need to list? X is equal to what? Negative 3i. If an imaginary root exists, its conjugate is also a root. So we bring them over. Add 5, subtract 3i, add 3i to both sides of the equation. So we have x plus 5 times by x minus 3i times by x plus 3i. And that's all equal to 0. So then from there we're going to distribute. Take my advice. Always multiply conjugates together first. It always helps. X times x is x squared. And I'm going to show all my work on this one. Plus 3ix minus 3ix minus 9i squared. From there I'm going to combine my terms. X squared, our middle terms cancel out. And then we have negative 9 times negative 1. I squared is equal to negative 1, guys. So negative 9 times negative 1 is positive 9. Does everybody follow me?
Yep.
So then we have that times, don't forget, we still have our x plus 5. And now we'll distribute that through. Don't make any errors here. X times x is x cubed. X times positive 9 is plus 9x. Positive 5 times x squared is plus 5x squared. Positive 5 times 9 is 45. So plus 45. Then I'm going to put it in standard form. X cubed plus 5x squared plus 9x plus 45. And we're done. So really not too horribly bad. Any questions on that? So you guys should be able to finish those up. 16 is not a requirement. If you can do that one, you're awesome. And you're done.
Great.